And of course, we first need to talk a little bit about our midterm exam first. So, so our my initial plan for midterm exam was the take home exam. So what it means is that I'm going to provide you the problems that you need to solve, and you prepare your answers in your home, and then submit your answer by by some specified time. So if 3 hours are allowed, then you are going to do solve problems in 3 hours and submit the answers. Mm, and of course, some students also uh, kind of provided some opinions and concerns about this type of a take-home exam, because this can be possibly this form of exam can be unfair, because some cheatings can be involved while preparing your answers. And of course, I also thought about that, but if I replace the midterm exam with some other homework, or if I completely cancel midterm exam, that means the students will lose some chances to intensively review what you have learned during the first half of this semester on this in this course. So my basic position is that we need that examination, that's midterm exam, and I'm going to proceed uh, as planned. So I'm going to provide you some. So the form of a midterm exam would be the take-home exam. I'm going to provide you some problems to solve, and by problems, it is not going to. And also, you need to provide the answers. But before talking about that, when we talk about the answers, uh, there are several things that I would like to ask you to prepare. So in this course, utilized several. Um, I utilized basically when I explain things instead of whiteboard, I utilized this word processor, specifically in this case Microsoft Word. And of course, because we deal with a lot of mathematical equations, so here, just like this one, we need equations. And my impression for several years is that students do not have sufficient capability in dealing with equations in this digital form. I mean, in Microsoft Word, or in when you uh, utilize word processor or some software for presentations, you have a lot of students experience the difficulties in representing the equations. So I would like to ask all of you to prepare for utilizing how to, for all of you to learn how to utilize the equation editor. So of course, in this case, as you might see, so during this online course, I utilized this equation editor so many times. So if you have watched these online lectures, then I hope you will also basically learn how to use it. So if so, another example would be, before talking about this. So about midterm exam. It is a kind of announcement, and or UN announcement. Do we need one or two? Sometimes this would be somewhat confusing. Let me check the dictionary. Announcement. I think we need two N's. Yes, we need two N's. So, announcement is there about our midterm exam. It is going to be, of course, next week. April, not April. It is going to be May, next Monday. So, May 4th, 2020. It is in the form of take-home exam. So problems will be uploaded by 3 o'clock p.m. on 3 o'clock p.m. on the day of midterm exam. That is May 4th, 2020. So you download the problem and you solve the problem. Okay, this would be the first. Second, you need to prepare midterm exam. To prepare the exam. Learn how to use equation editors and mathematical tools like MATLAB, or I'm going to allow you to use Microsoft Excel. So there are cases. So let me show you one example. So of course in our course we deal with the exponential functions many times. So when you deal with exponential function, then equation editors, you are able to use equation editors like exponential to the power So let's talk about that more specific case of radioactive decay. So equals minus lambda t would be not t, lambda and t would be the equation for exponential decay. And in this case, nt will be given as nt equals n0 exponential to the power minus lambda t. So that means you need to be able to write these equations in this kind of what is that? In this kind of Microsoft Word environment, or if you are familiar with the Hangul word processor. Then of course, so exponential distribution. So of course, here we are going to have, where is it? There must be some equation editor here. So control and M is going to be, will load us this type of equation editor. So what we can do is to d and t over dt equals minus lambda t, lambda nt. This is the function. And so if you are familiar with this, or if you are using this Hangul word processor, then of course you are also able to use this type of equation editor. So nt will be given as n0 exponential minus lambda t. Sorry. Exponential minus minus lambda t. Yes. So depending on which word processor you are using, also you have in your word processor you have this type of equation editors. So I'm asking you to be familiar with utilizing these equation editors. And second, so we have seen that we are able to use, we are able to draw the graphs with, so if we need to process a lot of numbers, then the mathematical tools will greatly help you. Or in some cases, if we need to draw some figures. So maybe I'm going to show you a very simple example. So I need to enlarge the size of a font to 18. Okay, so in case of exponential distribution, not distribution, exponential function. So then, maybe lambda, if you assign lambda as 1, then t equals from 0 to 0.0, and t is assigned like this, and then you may plot exponential function over minus lambda multiplied with t, with t and exponential function. and you are going to have a figure like this. So we also, during this course, I showed you this form of drawing figures several times. So I hope all of you are also quite familiar with utilizing these mathematical tools. And you may also, we are also able to add some labels like x equals t, y label as f exponential minus lambda, lambda t. And so we also add these regions, these labels, and also we may add some label like exponential function, exponential minus backslash lambda t. Oh. It's not label, I'm sorry, legend. So we just added the legend here. So be familiar with utilizing mathematical, these equation editors and mathematical tools. That would be kind of the thing that you need to prepare for your midterm exam. So, any question about midterm exam? So so this is a kind of announcement for our midterm exam. And also, there is another one that maybe most of you have already heard of that. But this, unfortunately, the university decided to extend online lectures to the whole semester. So initially it was planned to 2 weeks. After that it is extended to 4 weeks, and then it is extended to 8 weeks. So initially it was planned to 2 weeks, and then extended to 4 weeks, and then extended to 8 weeks, and then now it is extended to the whole 16 weeks. So it is quite unfortunate that we do not have any chance to have chance for face-to-face lectures. But of course, as always, this would be the decision that is made for the safety of all of us. But however, the final exam will be conducted in the offline way. So there would be offline final exam. However, I would add however here. So the lectures will be given in online, given in this way of online lectures for the whole 16 or 15 weeks, but the final exam will be conducted in the offline way. So due to some space availability issues, the period of a final exam can be extended to 2 weeks, but that's another problem. So when we take final exam, you should uh, come to our classroom and then prepare your answers while in the classroom. So, any questions about today's announcements about on midterm exam and this extension of online lectures to the remaining period of this remaining period of the semester? So if you do not have any other questions, then I'm going to proceed to proceed to maximum fuel temperature in the section of heat transport. So last time. So let's see where we are. Currently we are in section 8.3. So we already talked about all of this. And then so we were here. So calculating maximum fuel temperature. And so we started for calculating maximum fuel temperature, we started from the maximum. What would this Q prime mean? Q prime indicates the linear heat rate, but the amount of heat produced per unit length of nuclear fuel rod. So the maximum value can be found at the center of the reactor, where the position will be denoted as 0.0. R equals 0 and Z equals 0. So this maximum heat rate can be also calculated with the maximum heat rate will be proportional to the temperature difference between the fuel element and the coolant at that point. And this R prime Fe is the thermal resistance. And so we know that the maximum fuel temperature occurs at this point, and the issue is how can we calculate the temperature at R equals 0 and Z equals 0. So last time I tried to explain this, and then I had some difficulty in kind of mathematically formulating the equation. So let me show you how we can calculate this TC. So wait a minute, please. Oh, I just saw the chatting window and there are some questions related to our midterm exam. So let me also show you. So you need to cover chapter. So for midterm exam, of course, chapter 5. Chapter 5, all the topics that we have learned during the first half of this semester, and section 7.4. And also, we are going to finish chapter 8 today. And depend on the question of whether it is absolute evaluation or relative evaluation. So basically, so it is already announced that all the courses, the final, the evaluation will be performed in the absolute way. So that is the announcement given by the university. So, but of course, as I already, possibly I already talked about that, and I would like to provide at least some distinction between those groups who studied very hard on this subject, and also some other groups who did not do their best in studying this course. So of course, if you think, if the final result based on your accomplishment, you will be able to receive a very high grade. Also, if your accomplishment is not that good, then you are going to receive a very low grade. So of course, that does not, the absolute evaluation does not necessarily mean that you are going to get free. You are going to get very high grades for free. So if you did not study hard, then your grade will not be very good. And the third question is about how to submit your answers. Yes, answers should be provided in written form. With word processors, and also sometimes mathematical tool and file formats of mathematical tools like those one, MATLAB and Microsoft Excel. Sometimes as attachments. So you may think of submitting a report. So if you submit a report so if you provide some answers, if you submit a report, then you provide answers with all the supporting material. So let's assume that you are going to prepare. So it is like you are going to prepare a report on the problems that you need to solve. And any other question? And this is why because you will be asked to provide the answers with word processors or word processors. That is why you need to learn how to use equation editors, because in some cases you need to write equations. Any other questions? So then I'm going to, if you have any other questions, then leave your question in the chatting window. Meanwhile, I'm sorry. Let me see. It's section 7 point maybe 6. So yes, about the section related to the control rod. So yes, control poisons. I'm sorry, not section 7.4, it's section 7.6. Yes, thank you. So these were the topics and the sections and chapters that was covered during the first half of this semester. So all the chapters and sections will be included, and these will be the subject to the scope of a midterm exam. So let me also continue how we calculate the coolant temperature at the center of the reactor. So to calculate that, we also maybe there are things that we may refer to. So when we calculated the outlet temperature of coolant, so this was the outlet temperature. So to calculate that, Ti, the coolant temperature, the temperature of the coolant when it enters the bottom of the reactor, plus this would be the amount of temperature increase while traveling through the reactor in the axial direction. So this would be very helpful in understanding, in calculating what we would like to calculate here. So the temperature should be but here the difference is that we clearly have the position. So in the radial direction, r equals 0, and also we do not calculate the temperature at the top of the reactor. We would like to calculate the temperature at the center of the reactor, just halfway through the reactor. So in terms of z, you should start from minus h over 2 to not h over 2, it should be 0. So because 0 is the position that we would like to calculate the temperature, the coolant temperature. So after that, what is Q prime RZ? That is the linear heat rate. So linear heat rate. So at least we know that R is specified as 0. And Z starting from minus h over 2 to 0. So during that course, we would like to integrate all the heat that the coolant would receive. and then that will be used to calculate the temperature of the coolant. So what about Q prime 0G? So I'm going to, instead of Q prime, let's try to find out the equation for this. So linear heat rate. So at the beginning of heat transport, we started from linear heat rate. And here I would like to also fix one thing. So I wrote this as Q prime dot dH, but in fact the parameter in actual direction is not h. It should be corrected to z. So also all dH need to be corrected to z. Also dg, dg, g, and dz. So this is one correction that we need to make. And Q prime dz is also, if we follow this, then it is given here in this way. So P over V, and then it eventually became P over NH, FR, FG, and DG. So we are going to use this. Of course, this would be the Q prime part. So Q prime is now replaced with this. Q prime is replaced with that equation. One thing is that R is already fixed as 0. So in this case, P over NH is a constant that can be taken out. And F prime 0 is also a constant with respect to z. And in fact, F prime 0, if we use our knowledge that the FR0 is the maximum value. It's kind of a peaking factor in radial direction. So in fact, this should be written as radial peaking factor. So, and I'm going to move H here. So H will be placed here. And N is going to be with WCH. WCH is the mass flow rate of the coolant for a single channel, and N is the number of channels. So if we multiply that, that is going to be total amount of coolant that is flowing per unit time. In other words, this will be simply mass flow rate of coolant. So I'm going to move P here, and this one, we do not need this. So equation is now given in this form, and I'm going to take a bracket to here. So what would be the integration? 1 over h and integration from minus h over 2 to 0, fg and z. Then what would be the fg? What would be fg? So we may refer to chapter 7, or in earlier in this book we have chapter, we have this equation 8.19. Of course, this equation 7.27 will give us the exactly same equation. So in fact, 1.57 come from half of pi. So FG can be rewritten as cosine. Basically, it is cosine function. First, pi over 2 cosine, and if you see the equation, cosine pi over 2 pi h pi z over h. So this is in fact Fg. And what would be this integration? The result of the integration. And integration from minus h over 2 to 0 with cosine function. So in fact, so let me, at this point, this can be written as so pi, because pi is simply constant, it may enter here. H, because it is a constant also, it may enter here. So 1 over 2 remains, and in fact 1 over 2 is a constant. They can be taken out. So it is like a cosine t. It is very similar to cosine t dt. Integration from minus pi over 2 to 0. So that integration is simply, that integration would be 1. So this whole bracket will be same with, because this integration is 1, what we are going to have is just 1 over 2. So the final result would be, so we have 2, 1 over WCP, P and FR plus TI. So this would be TC, the maximum temperature of the coolant. And we need this. So instead of TC, maximum coolant temperature, we are going to insert this part, this equation. Not, in fact, this part, TC 0. And this will be same. So this is how Q prime max is given in terms of maximum field temperature and all other parameters. And in fact, this Q prime max will be same with the maximum heat rate. So how can you calculate that? P is total amount of heat. And if we divide this with NH, because NH is total, kind of total length of all control rods. So this is just one field rod, and there are n fuel rods. Now, a single fuel rod will have the height h. So if we have n number of fuel rods, then the total amount of total length of fuel rods will be nh, and that's the heat P. The total amount of heat is produced in the controllers because not controllers. So the total amount of heat P is produced with fuel rods whose total length is nh. So that means P over nh here so P over nh is kind of an average. So average is linear heat rate, and maximum heat rate can be calculated by multiplying first the radial peaking factor and axial peaking factor. So if we rearrange this part of the equation, then we will be able to calculate the maximum fuel temperature. So maximum fuel temperature is given. So this would be the right hand side. We are going to multiply this with thermal resistance for a single fuel element, and then plus the remaining part. So here we are going to rearrange the equation. So I'm going to move P to here and use F prime, R prime here. And then take a parenthesis and take P out. So I'm going to take P out, and what is this? R prime Fe divided by NH. So if you see equation 8.31, if we move our text yet, that is RF. That's reactor core thermal resistance. So that is the thermal resistance for the whole reactor core. So this can be replaced by R prime. Now RF. So now we have the maximum fuel temperature. That is given, the same equation is also given as equation 8.44. Right here. Now we have the equation for TF, the maximum fuel temperature. Next, we are going to think about the temperature drop. From fuel to coolant. And kind of fix this as temperature drop ratio from coolant to between from coolant to temperature and from to temperature and from coolant, not coolant to, I mean the average coolant temperature to inlet coolant temperature. So if I write this equation, so what I want to say here is this: I would like to compare the temperature drop between fuel temperature. So average, this would be average fuel temperature. So temperature drop from fuel to coolant. This would be the average coolant. So wait a minute. So that's the difference between average fuel temperature and average coolant temperature. And we would like to calculate the ratio between average coolant temperature and inlet temperature, inlet coolant temperature. That is denoted as Ti. So how can you calculate this? So if you see equation 8.32, equation 8.32, TF minus TC, the numerator part, is given as RFP. So this is RFP. About the denominator, the difference between average coolant temperature and inlet temperature, coolant inlet temperature, we have equation 8.40. So equation 8.40, we have so if we move Ti to the left hand side, we are going to have P over 2WCP. So what we are going to have is P over 2WCP. So this P in the numerator and denominator cancels out. So what we are going to have is 2WCP multiplied with RF. So that's equation 8.45. And I think about the difference between fuel temperature and coolant temperature. This would be several hundred degrees Celsius. Sometimes 500, 600 degrees Celsius. This would be around 300 degrees Celsius. And so we have several hundred degrees Celsius in temperature difference in the numerator. In case of denominator, the difference between average coolant temperature to coolant inlet temperature would be like 300 degrees Celsius minus 290 degrees Celsius. So this would be just the order of 10 degrees Celsius or 20 degrees Celsius. So if we compare the ratio, then this ratio would be certainly much bigger than 1. So this property is very important because this will be used later in our analysis. So, and also we have others like so this is equation 8.45, and so the remaining paragraph explains the relation between the thermal resistance of the whole core and the thermal resistance at the center line, and it is given, this relation is given in appendix D, so you may refer to appendix D about this. And we are going to move on to the pressurized water reactor example. So this is about how we this is of course somewhat simplified, but it can give us how nuclear reactor design is performed with the parameters that is already already fixed, or those parameters that is already determined. So based on that, it provides us how the design process will look like. So let's see this equation one by one. So the power is given as 3000 megawatt thermal, and moderator to fuel ratio is given as 1.9. So if you remember what we have learned in maybe in chapter 4, the optimal ratio would be around 2.0. So in this case, this ratio is given as 1.9. So maximum heat rate is determined as 400 watt per centimeter. So if we exceed this linear heat rate, then of course the integrity of a nuclear fuel can be challenged. And also about surface heat rate. Surface heat rate should be maximum surface heat flux is given as 125 watt per centimeter squared. So of course, if the surface heat flux is bigger than this, then the integrity of a nuclear fuel can be challenged. The inlet coolant temperature is given as 290. Outlet coolant temperature is given as the maximum outlet coolant temperature is 330. So with this, first, this example asks us to calculate some physical parameters like fuel radius and lattice pitch and so on. So we are going to examine these one by one. So pressurized water reactor example. First, fuel radius, which is denoted as A. So to talk about fuel radius, we have two parameters. The maximum, the maximum linear heat rate and maximum surface heat flux. If we see the figure that is drawn in PowerPoint, so with just the heat generated by, so the amount of heat produced per unit length should be transferred, should be transported to the coolant that is flowing around the nuclear fuel. So that means the maximum linear heat rate is directly related to the maximum heat flux. So the relation would be so Q prime will be the linear heat rate, and by right and this will indicate its maximum value. This maximum value multiplied with some very small height. So that's the total amount of heat generated. The total amount of heat generated for this dg. How can I say that? So if we think about that kind of a fuel element, so if the height is given as dg, while Q prime is produced per unit length. So the maximum heat, so in the place where the heat is produced, the maximum value, so maybe that is the center of the reactor. This Q prime will occur at the center of the reactor. And then if this would be the amount of heat produced, because this is a linear heat rate, if we multiply dg, that is going to be the maximum amount of heat produced for this very small volume, and that heat must be transported through the surface of the fuel rod. So this maximum value should be the amount of heat produced must be smaller, in fact, than so Q double prime max is going to be the maximum surface heat flux, because all the heat produced inside of that volume need to be transported through the surface of the fuel rod. So this value should be smaller than Q double prime max multiplied with, so what would be that, once again, what would be the area, the total amount of area that the heat should be transported? because the radius is a, so 2 pi a multiplied with dz is going to be the amount of area that heat can be transported. So q prime max multiplied with 2 pi a, and dz is going to be the amount of area, that is the area that the total amount of heat needs to be transported. So of course in both sides we do not need dz, so we will have the relation between 4a. So from here a can be calculated. So if we write that down, a should be so we do not need dg, and this should be divided q prime max multiplied with 2 pi if we move this. So radius should be bigger than this value. That is the restriction given to sphere radius. What about the lattice pitch? So about lattice pitch, so this length, so this is a single lattice, and the length of this lattice would be called as lattice pitch. And so the equation, the relation that determines the lattice pitch P will be so this would be the volume taken by the fuel rod, and this would be the volume taken by both the fuel rod and coolant. And it was already determined that, of course, this volume is already fixed, and then with this value of fuel volume, we are able to determine the volume taken by the coolant. And previously, that volume ratio should be given as 1.9. So in other words, the restriction that is already given is that the volume ratio for the coolant, H2O, over the volume of the fuel, the volume taken by UO2, should be 1.9. So the volume taken by UO2 would be pi a squared. Pi a squared. The volume taken by the coolant would be p squared. That's total area minus the volume taken by the fuel. And it is already fixed as 1.9. So because when we fix the field radius, then we will be able to determine P. So next would be the core volume. So core volume So core volume is in fact restricted by the maximum linear heat rate. So once again, if we go back to this part of field rod, the point where the maximum amount of linear heat is produced. So then the amount of volume that we are going to need is this linear heat rate multiplied with P squared and multiplied with dg. This amount of volume should be that's the amount of heat produced per unit so this is already confined in this lattice, and this would be the volume taken volume considering both field rod and the coolant. And because this is the maximum value, the actual amount of heat produced should be less than this. So because this is the maximum value, this should be the actual heat produced. So this is the volume rate, the average power produced in the reactor. And if we multiply, let me have this here. So this would be so if we multiply the radial peaking factor and actual peaking factor, that means the maximum heat produced per unit. In this case, the maximum heat produced per the volume that we consider here. So that maximum value would be calculated as, so this average value is given as total volume divided by V and multiplied with FR and FG. So in this way, we are able to calculate, we are able to find the relation between the volume of the reactor and the power of the reactor and maximum linear heat rate of the reactor, while utilizing this P squared, the area of a single lattice cell. So it is already 4:16. So we are going to take a short break until 4:31, and then we are going to continue. First, this pressurized water reactor example, and then we are move on to thermal transient section. So we are going to resume today's lecture at 4:32. And also, I would like to ask all of you to leave your name for checking your attendance. So when I wrote this equation for related to core volume, I realized that I could not completely make sure whether this equation is correct or not. So in fact, it should be corrected that if you look at this figure, then of course this fuel rod, or this small portion of a fuel element, is located inside of this lattice cell. So this is just a part that is taken from a single control rod and a single lattice cell. Simply the height is dz. So maybe this is the one at the center of the reactor. And in fact, the correct relation would be the total amount of heat produced inside of produced by this dg length of control rod, the fuel rod, would be, actually we need to delete this part, and it should be q prime max dz. That's the amount of heat generated by fuel rod. And this fuel rod should be taken, that is going to be the average heat, that is average power, and basically this is the peak power. So because this is the amount of heat generated per unit volume, so we need to multiply the volume. So multiply with p squared with the dz will give us the volume. The volume of the reactor that needs to be the volume of the reactor that this heat is produced. And because P triple prime, the average heat per unit volume is given as P, the total heat divided by the volume of the reactor. So if we multiply this, then now we have the relation between the volume of the reactor and the maximum linear heat rate. Of course, it is going to be, so that means the volume of the reactor should be, so in both sides we do not need dz, and if we move v to the left hand side and q prime max to the right hand side, then the volume should be bigger than this. And if this is the volume, then we are able to determine height of the reactor. The condition is that the height is the same with the diameter. Of course, the diameter is twice of the radius. Ah, before talking about this, there's one thing that I missed when I talked about midterm exam. Of course, this is something that we do not need to talk about, but of course, no cheating is allowed. That means you should not ask others answers. Also, you should not share your answers. You should not even have discussions on the problems. So that means you should solve the problems yourself. So no cheating is allowed. You should solve the problems yourself. So this is also, of course, the last thing that I wanted to add related to our midterm exam. So, because this is an examination, you should solve the problems all by yourself. So let's go back to the pressurized water reactor example. So about how can we, so the volume is already determined. The volume, so if we fix the volume, then of course this height can be determined by considering that this volume is given as pi r squared h, r squared and h. And we know the relation between r and h. So because r is given as half of h, so it can be found that 2 pi and h cubed. Oh, I'm sorry, this would be 4, not 2. What about core average power density? Core average power density will be here. Core average power density should be given as power divided by volume. And if power is already given, and when we calculate when we fix the volume, then core power density can be determined. Next, the number of fuel elements. So the number of fuel elements. So we are going to, so when we see the upper part of the reactor, then we already determined the pitch of a single lattice. So we already determined that P, and we need to and that means we already determined the volume, the area. We already determined the area taken by a single lattice cell. And how many lattice cells can we place in the reactor will be determined actually by, so pi r squared will be the total area, total cross-sectional area of the reactor, and that should be smaller than the total number of field elements multiplied with p squared would be the cross-sectional area taken by a single lattice cell. So as you can see, just like this one, so all the lattice cells will be placed inside of the reactor. So this equation should be satisfied, and with this we will be able to determine the number of field elements, or the number of lattice cells that can be placed inside of the reactor. What about mass flow rate? So when the number of lattice cells are determined, that will be the number of channels that the coolant may flow. And see, this should be determined by, so I'm going to copy this, and what I want to use is the maximum outlet temperature. So T outlet max is already fixed. That means the total amount of so because the maximum outlet temperature, of course the maximum outlet coolant temperature will place at the center of the reactor core, and then that should be limited. That means the coolant, because the power is already determined. So the relation between Ti, the inlet temperature, and the amount of coolant that is flowing through the reactor will determine the outlet temperature, in fact the average outlet temperature, and then the maximum outlet temperature will be determined by multiplying the radial peaking factor. So what I'm saying is that, so this maximum temperature should be, so in terms of Ti, that is the inlet temperature of the coolant, plus the temperature increase while going through the temperature increase while going through the reactor in the axial direction would be total amount of heat divided by the mass flow rate and specific heat of coolant. And this would be the average temperature. So average temperature increase and the maximum temperature increase. The maximum temperature increase can be determined by multiplying the radial peaking factor here. So with this, we are able to determine the mass flow rate. So if you move Ti to the left hand side and then multiply W to both sides of this inequality, then you will get the inequality that the maximum flow rate should be bigger than some value. We are also able to determine the mean coolant velocity. So mean coolant velocity. So by using this maximum flow rate, so maximum flow rate will be same. So also, once again, if you look at this figure or this one, then for a single lattice cell, then the area, then of course first we need to calculate the volume taken by the coolant, and to do that we first need to calculate the cross-sectional area. So P squared minus the area taken by the ferrous minus pi a squared would be the area taken by the coolant. And if we multiply the mean coolant velocity, then so mean coolant velocity is the height, the amount of the distance that a coolant will travel divided by the time. So this would be actually, if we multiply cross-sectional area, that is going to be the volume that the volume that goes through a specific cross-sectional area divided by time. So this is basically the volume divided by time. And if we want to calculate the mass flow rate, the mass divided by time, then we need to multiply the density of the coolant. And this is going to be just for a single lattice cell. So if we multiply, if there are n number of lattice cells, then this is going to be mean coolant. This relation for mass flow rate will give us the mean coolant velocity. So now we are going to move on to section 8.4 about thermal transients. So in section 8.4, we are going to, because as the name transient says, we are going to deal with the temperature of fuel and coolant as a function of time. So if some transient situation occurs, then we would like to calculate how the temperature of the fuel or the temperature of the coolant would change as a function of time. So for that purpose, we are going to see the textbook first. So if there is no cooling at all, then the total amount of power will be used to increase the temperature of the fuel. So MF is the mass of the fuel, and CF is the specific heat of the fuel. And if there is no cooling at all, then all the power, all the heat generated will be used to increase the temperature of the fuel. However, if we also consider that some amount of heat is transferred from the fuel to coolant, and the amount of heat that is transported is the temperature difference divided by RF, the thermal resistance of the core. So for the total amount of heat, total amount of power, some power or some energy, some heat is transported to the coolant, and the remaining energy will be used to increase the temperature of reactor core, temperature of the fuel. So it can be called as approximate lumped parameter model. And so the basic equation, if we write it once again, then this would be mass of the fuel and specific heat of fuel, and the average fuel temperature. dT is the change of fuel temperature. So once again, if we do not consider the energy that is transported to the coolant, then it can be simply written in this form. But if we consider the amount of heat, that is actually minus the amount of heat that is transported to the coolant, then only the remaining energy will be used to increase the temperature of the fuel. So also the amount of coolant, the amount of energy or the amount of power, heat that is transported to the coolant is given as the difference between fuel and coolant divided by thermal resistance. That is the amount of power that is flowing from fuel to coolant. So if we divide this So if we divide both sides with 1 over, so if we divide this with 1, so divide both sides with MF and CF, and here we are going to have MF, CF, and RF. So it is given minus, we are going to define a parameter called tau. So of course tau will be same with MF, CF, and RF. And that is called as core thermal time constant. So tau, which is same with MF, CF, and RF, is called as core thermal time constant. Then only the numerator. Yeah. So this is equation 8.49, and thermal time constant, this is 8.50. And first we are going to see some examples of a fuel temperature transient. And before talking about that, about this thermal time constants in the textbook, what we can see in our textbook is that the tau, and about this tau, the value of tau is typically the order of a few seconds, and larger for oxide than for metal fuel. So and it is a measure of the time required for heat to be transported from fuel to coolant. So that is a kind of a measure then how long it will take how long it will take that of some heat is transported from fuel to coolant. So just like when we talk about the radioactive decay, we used the decay constant lambda. So just like that. So that lambda also indicates how fast radioactive decay occurs. So just like that, by using this tau thermal time constant, we may determine how fast heat is transferred or transported from fuel to coolant. So we are going to see some examples by using this tau. So there are some fuel temperature transients, and when we have some step change, that means reactor power suddenly changes from some constant value to 0. That would be the first case. So instantaneously. So that means previously Richter was operated at the some power level, and then all of a sudden Richter power becomes 0. So from P0, so from some constant power P to 0. So in that case, after the reactor is shut down, then the equation is that, so from this equation, now PT, reactor power, is now reduced to 0. That means we do not need this part of the equation. So this is simply minus 1 over tau and TF minus TC. And if TC does not change significantly, so during that time, for a very short time, TC can be approximated as constant. So compared to the time that TF changes, the change of average coolant temperature will not be that significant. So if we compare the difference, then the change in coolant temperature will not be that significant compared to the change of fuel temperature. So this part can be considered as constant. So now we have only function for fuel temperature, and the result will be an exponential decay function. That is also given in equation 8.52. So the solution can be found here. It is simply exponential decay starting from this temperature, Tc. So next case, what about sudden power jump from 0 to some constant power, P0. Let's write it as P0. So after the power is increased, then the PT should be P0, and P0 is also a constant. And we are going to assume that initially TF, the field temperature, so we are going to assume that the reactor did not produce any power. So because of that, there is some equilibrium between the temperature of the fuel and the temperature of the coolant. So that means initially fuel temperature at time 0 can be, it is assumed that it is the same with the coolant temperature when the reactor did not produce any power. So in that case, so the reactor power is suddenly changed from 0 to P0, while it is a function of, and Tc is also considered to be constant in this case also. So to be more specific, I also would like to add this condition here. So coolant temperature almost remains constant. So this is also another form of differential equation that is quite familiar to all of us. So the result will be 1 minus exponential form. So if we see the textbook, then the fuel temperature is given as coolant temperature plus this constant and exponential minus 1 minus exponential form. And also one more thing. So in this case, 1 minus exponential minus tau over t can be also approximated as 1 minus t over tau when time is very small compared to this time constant. So also the fuel temperature can be approximated like this. So the advantage of equation 8.55 is that it has some linear relation. So starting from so initially, because there is no Richter power, no power is produced from the nuclear fuel, from fuel rods. So the temperature of the fuel is the same with the temperature of coolant. And as the fuel produces power, then in a very short time, it can be also almost, it can be with this approximated relation. The P0T is the total amount of heat produced during that time from 0 to T. And if we divide this with MF and CF, that means the mass of the fuel and specific heat of the fuel, then what will be remaining would be the temperature difference. So if we remember, so mass specific heat multiplied with the temperature difference equals the total amount of energy. So we have a total amount of energy here divided by mass and specific heat. That is going to be the increase in temperature of the fuel. So we can see this linear increase in temperature here. So next thing is coolant temperature transient. So I'm going to take this equation and slightly modify to write the coolant temperature, the equation for coolant temperature transients. So mass of coolant and specific heat of coolant multiplied with the change of coolant temperature is given as first. So previously, this was the amount of heat or energy, that is amount of power that is transported from fuel to coolant. And when we establish the equation for coolant, then this is going to be the power that is given from the fuel in the viewpoint of coolant. and some heat or some power, because the continuously power is transported. I mean the role of coolant is to receive power from the fuel and then deliver it to the steam generator in case of pressurized water reactor. So the role of coolant is to deliver its power to some other places. So while doing that work, if it receives a lot of power, and then the average coolant temperature will increase. So the amount of this would be the amount of energy that it received from the fuel, and some energy, some power, if some power is used to increase the coolant temperature. So that means, and so that so once again, this is the power that is received from the fuel in the viewpoint of the coolant, and some power should be delivered outside of reactor coolant system, and that amount of power is W, the mass flow rate, multiplied with Cp is the specific heat of the coolant, and multiplied with, so we first, what would be the outlet temperature? Outlet temperature of the coolant, so the amount of, the outlet temperature of the coolant will be, in fact, inlet temperature plus twice inlet temperature plus the twice of temperature increase between the inlet temperature and average coolant temperature. So where should we, outlet temperature and so this would be Tc minus Ti, because the average coolant temperature is the temperature. So you may think about this. So if the inlet temperature is 290 and if the outlet temperature is 330, then the average coolant temperature would be the average between inlet temperature and outlet temperature. So it is going to be about, so if the inlet temperature is 290, the outlet temperature is 330, then the average temperature would be 310. So if you think about this relation, then if you want to calculate the difference between outlet temperature and inlet temperature, you are able to calculate that with first calculating the difference between average temperature and inlet temperature here, and then multiply it with 2. So coolant temperature, so the equation for coolant temperature is now given in this form. So with this we are able to calculate, maybe we divide this with 1 over with MC and CP. So 1 divided by this, and then also once again we divide this with this, and in case of 2 is now is moved to here, and then this 2WCP can be moved to the from numerator to denominator. So I'm going to first move it to the denominator, and RF is now moved to here. So then this will be simply written as TF T minus TC. So that's equation 8.57. Oh, 58.58. And this is simply, so this will be replaced with T prime, tau prime, tau prime, and CP. Well, so all this part is now called as tau double prime, tau double prime. So this was how tau was defined. Tau prime was defined, and if you remember that, so previously we defined tau. So previously we defined tau with this. So that means tau divided by this would be 1. So what I'm saying is that even though because we multiply just 1, and because the definition of tau tau is this, so this can be maintained. So here what we can see is the RF in the numerator and denominator cancels out. So we just have tau here, and in front of tau we have MCCP and MFCF. MCCP in the numerator and MFCF in the denominator. About tau double prime. So it is basically defined with this relation. And so what about the relation between MC and W? MC and W. So I think the relation, the MC, the mass of the coolant. So if you think the coolant that is filled inside of this reactor, that will be same with the area that this coolant flow multiplied with the height of the reactor. So this would be the volume that coolant will flow. If we multiply the density, that is going to be the mass that is taken by coolant. And what about mass flow rate? Very similarly, mass flow rate. So to be specific, I'm going to write rho as the coolant of coolant, the density of coolant. The way we calculate mass flow rate is the area of flow, and then if we multiply average velocity or average speed of the coolant. And this would be the average volume. This would be the volume that is passing through some specific cross-section of the reactor. So for example, this would be the volume of the coolant that passes through the bottom of the reactor. And if we, of course, in both sides it had Cp. So if that is the volume that passes through the bottom of the reactor, and if we multiply the density of the coolant, then it becomes the mass flow rate. So from here, what we can see is that we may cancel omega c, the rho c, the density and the cross-sectional area of the flow of the coolant flow. So if we delete this, then what we are going to have is h over 2 Vc. So we are going to delete 1, 2. So what this tells us is that, of course, the average velocity of coolant is the distance divided by time. So it can be also rewritten as the height of the reactor divided by the time that is taken for coolant to pass through the reactor from the bottom to the upper part of the reactor. So now this becomes Tc divided by 2. That is the half of the time for the coolant to pass through the reactor. And when this is approximated, the change of coolant temperature, of course, it is always less significant than the change of fuel temperature. So if the left-hand side, this part, is considered to be 0, then what remains? So from this equation, so this should be equal. So we may delete MCCP, and 2WCP will be here. 2WCP, and if we move RF to the right hand side, so this would be the relation between fuel temperature and coolant temperature. And from here we are able to calculate what Tc is. So Tc is going to be, if we move the Tc in the left hand side to the right hand side, it is going to be 1 plus 2WCPRF. Of course, this 1 comes from the Tc in the left hand side. Or maybe I can add one more line here. So TF equals, let me 1 plus 2WCPRF and Tc and minus 2WCPRF multiplied with Ti. So we are going to move this term to the left hand side and then divide it both sides with this one, then over 1, and then take a bracket here, plus the right hand side. Tc is given with this equation. And so previously RFWCP, previously it was mentioned that this is much significantly bigger than 1. So that was equation, let's see, that was equation here, equation 8.56. When we compare the temperature difference between fuel and coolant outlet temperature and coolant inlet temperature. So because this is significantly bigger than 1, so this one can be ignored. So by approximately this can be given. So 1 is significantly smaller than 2 WCF. So what happens here is that plus these will cancels out. So plus only TI remain here. So why do we do this? Is that by calculating TC, so by writing TC in terms of TF, so we are going to delete this TC term here. Then we are going to simply have, or if we move further, so this is the relation. So here we have TF, of course this would be function of time, and we have this TC term, the coolant temperature term, the average coolant temperature term, and we just found that TC can be represented with TF, or TC is given as a function of TF. So now it becomes much easier for us to find the TF. So TC is given. So we may use this relation. So 1 over TF, and see, so it uses TF minus, so TC, TC is given as so we are going to use this. So what will remain here is that 1 minus, and here, so we originally had this, and minus 1 over tau, and here what we are going to have. So let me first place a bracket here, and in terms of TF, 1 minus this part. So only so what will remain is, in the numerator we are going to have only 2 WCPRF. So you may, instead of 1, can be considered as, this would be 1, and minus 1 was calculated. So what will remain is only this. So this is what we have for CTF, and what we realize is that about Ti we have the same term minus we have the same term here multiplied with Ti. So it looks quite complicated, but what we realize is that this constant can be taken out, and now we have the difference between field temperature and the coolant inlet temperature. And this will be called, so by adding all these parts, so tau multiplied with, so let me write it in this way, power multiplied with all of these will be simply called as tau double prime so this will be called as tau double prime. And we are going to use this. We introduce this new parameter. So it is simply tau multiplied with this parameter. And one thing that we should remember is that this WCPRF is much bigger than 1. So this whole part, it can be approximated as 1 because this one can be, the 1 in the denominator can be ignored. So what we realize is that tau 2 prime is very similar to tau. So that means also this relation, this equation can also be approximated. Instead of tau double prime, we may use tau here. So what we have is that so if we compare this equation with equation 8.49, the only difference that we can find is that Tc, coolant temperature, is now replaced with Ti, the coolant inlet temperature, of course, which is a constant. So now we do not need to use some approximated relation, related to Tc, but now this is an equation only for Tf, the average field temperature, and the power change. And with this, if power is given, then we will be able to calculate the change of field temperature. So this would be, let's see, there is one more equation. So the coolant temperature is given as Ti divide by 2 RFWCP. So 2 prime. So what about the last equation? 61. Let's see. So from this equation, so 8.64 is in fact same with this relation. So Ti plus 1 over 2 WCPRF and average field temperature. So equation 8.64 is already given. So that equation is already covered. And then now we already covered all the topics in chapter 8, energy transport. And as I already announced, next week we are going to take a midterm exam, which is conducted in the take-home exam form. And I also one more time I would like to emphasize that no cheating activity is allowed. And so my warning is that if some similarities are found between the answers of two students, then I will not distinguish which one is the original version and which one is the copied one, because the two students will have the same consequence. So good luck for your midterm exam. I hope you review all the topics that we covered and then study hard and well prepared, and you are going to you will be able to provide nice answers for the problems. So next week midterm exam, and good luck for your midterm exam.